So today we are going to discuss convolution theorem for Laplace transform. Okay, and we shall see some examples of this. So convolution theorem, let Laplace transform of capital F be small f and Laplace transform of capital G be small g. Then if I multiply small f and small g and take the inverse Laplace transform, it should be equal to this integral, and this integral is called the convolution of capital G and capital F. That is integration from 0 to t, g of tau, f of t minus tau, integration with respect to tau. So the final answer will depend only upon t. Tau has been integrated over. And we can interchange f and g. So instead of g, we can write f here. And instead of f, we can write g here. And this, this is called convolution, and it is denoted by the asterisk symbol. Okay, it is denoted by the asterisk symbol, and asterisk symbol stands for convolution. Okay, so let us try to prove this. The Laplace inverse of small f, small g is equal to the convolution of capital G, capital F. So since small g is the Laplace transform of capital G, we have this expression. Okay, so small g is equal to integration from 0 to infinity e to the power minus s tau g tau d tau. Here the integration variable can be represented by any variable, tau, t, omega, whatever, any variable that we want. Now we multiply both sides of this equation number 1 by f of s. So let me use the drawing tool here. So we multiply both sides by f of s, this f of s. Then we bring f of s to the front here. So we have e to the power minus st f of s. Okay. Then using the property, that is Laplace transform of f of t minus t naught, u of t minus t naught is equal to this. This is the time shifting theorem. We use this property here. So we use this property here in this expression. So instead of e to the power minus s tau f of s, instead of e to the power minus s tau f of s, we can write this as the Laplace transform of f of t minus tau, the unit step function of t minus tau. And Laplace transform of this is by definition, let me clear all drawings. And Laplace transform of this is by definition e to the power minus st f of t minus tau u of t minus tau. Okay, this we write as equation number 3. Now we substitute this equation. So e to the power minus s tau, this part we substitute from equation number 3. This right hand side of equation number 3. Then we get fs gs is equal to, so we get fs gs is equal to this particular integral. Okay, so we have brought this part here, dt. Okay, now let us look at this u of t minus tau. Let us look at this function. This function is 0 when t is less than tau, and this function is equal to 1 when tau is less than t. I repeat, this function is 0 when t is less than tau, or tau is greater than t, and this function is 1 when tau is less than t. So in this integral, look at the tau integral. tau integral, tau, g tau, then this tau integral, tau from 0 to infinity. For tau greater than t, it should be 0. So we divide this interval tau from 0 to infinity into two intervals. One from tau equal to 0 to t, and second from tau equal to t to infinity. And for tau from t to infinity, this function is 0. So that means the only remaining term is the only remaining term is this integration of tau from 0 to t. So this u will give this f t minus tau, u t minus tau, g tau will give us this integration. Okay. And this term inside the bracket, this is nothing but the convolution of g and f. Convolution of, I repeat, f and g. You can also say convolution of g and f. So in other words, f of s, g of s is equal to the Laplace transform of the convolution of f and g. Okay, that is here. So f of s, g of s is nothing but the Laplace transform of the convolution of f and g. So if you take the inverse Laplace transform of both sides, we get the required result. That is this result. Inverse Laplace transform of f of s, g of s is equal to ft gt. Okay, so that is how we prove the convolution theorem. And the convolution process is associative with respect to the two functions gt and ft. That is, we can, these two terms are equal. This integral is equal to this integral. Okay, this is associative with respect to ft and gt. Okay, let us look at one example of this. Find the inverse Laplace transform of 4 by s square all into s minus 2. The solution, we know that this 4 by s square fall into s minus 2, this can be written as the product of two terms, 1 by s square and 1 by s minus 2. So inverse Laplace transform of this is simply t, and we can call it capital G of t. And inverse Laplace transform of this is nothing but e to the power twice t. We can call it capital F. So the inverse Laplace transform of this will be 4 times the convolution of g and f. So by definition of convolution, this would be g tau. So gt is equal to t. That means g tau will be equal to simply tau. And f of t minus tau, we replace here t by t minus tau. So we get e of e to the power twice t minus tau, d tau. Okay. So Laplace inverse of 1 by s square is t. Laplace inverse of 1 by s minus 2 is e to the power twice t. So we take the convolution of these two, that will give us the inverse Laplace transform of this. And this we integrate by parts. We take tau as the first function, e to the power twice t minus tau as the second function. So this is first function multiplied by the integral of the second function minus differentiation of the first function multiplied by integral of the second function. Okay. So at tau equal to t, this first term, it reduces to this this expression, and I'm sorry, at tau equal to t. Okay. So 4 and minus 2, we get minus 2 here. When tau is equal to 0, this whole term is equal to 0. When tau is equal to t, this becomes e to the power 0. Okay, so this term become 1 and we get t. So we get minus twice t. And this integration, we get twice e to the power twice t minus tau by minus 2. Twice because we have half here and 4 here. So half and 4 we get twice. Then take the limit from 0 to t. Now when you put t equal to, when you put tau equal to t, this would be t minus t, that is e to the power 0. So that is 1. And when you put tau equal to 0, this becomes e to the power twice t, and you get the second term. So this is the final answer for a given problem. Very simple, straightforward application of the convolution theorem. Now let us look at another application of the convolution theorem, that is to solve the Volterra integral equation. The Volterra integral equation is given by this equation. Capital X of t is equal to f of t plus integral a is some function of t minus u xu du. This is nothing but the convolution of a and x. So if I take the Laplace transform of both sides, the Laplace transform of capital X is small x. The Laplace transform of capital F is small f. And the Laplace transform of convolution of two functions is nothing but the product of their Laplace transform. So Laplace transform of A multiplied by Laplace transform of X. Now we bring X towards the left hand side. So we have 1 minus A times X. And we divide both sides by 1 minus A, we get X equal to f of s by 1 minus AS. Okay, so as an example, solve for xt which satisfies this equation. This is nothing but this is the convolution of sine and x. So if I take the Laplace transform of the given equation, I get x of s equal to 2y. The Laplace transform of t square is 2y s cube. Laplace transform of convolution is nothing but the Laplace transform, the product of their Laplace transforms. So sine t Laplace transform, x t Laplace transform. And this is nothing but 2 by s cube, and Laplace transform of sine t is 1 by s square plus 1 xs. Now I bring this term 1 by sine square plus 1 xs towards the left. Okay, so I get so I get x of s equal to twice s square plus 1 by x to the power 5. This we get after simplification. Okay, so we bring this towards the left, so it becomes 1 minus 1 by s square plus 1, and when you simplify that, we get this expression. And this can be written as two terms, that is 2 by s cube plus 2 by s to the power 5. And now if I take the inverse Laplace transform of both sides, we get x of t is equal to inverse Laplace transform of this is t square, and inverse Laplace transform of this is 1 by 12 t to the power 4. So this is how we use the convolution theorem to solve Volterra integral equation. I think that is all for today. Let me stop recording.